of electronic degrees of freedom can be calculated by solving the equation motion according to this equation. And here this term indicates fork matrix. Here this term indicates the density operator, and this is dissipative transitions. And for the fork matrix, we have three components. The first one is ground-state fork, and the second one is adiabatic coupling. Third one is electromatter interaction. And this electromatter interaction term is time-dependent, but by applying some approximations, we can treat it as time-independent. So based on Rabi theory, consider transitions between I and G. The Rabi frequency is related to transition dipole moment and the intensity of electrical field. So due to the optical-driven Rabi oscillations, there are hubs in the matrix of density, in the elements of density matrix. So we have this stepwise change in the occupation of two participating orbitals. So with these equations, we can update the total electron density. With new electron density, we can update the interatomic forces. And with new forces, we can get the position of ions. So in such a way, the electronic degrees of freedom and the nuclear degrees of freedom are coupled. Okay, so this time I'm going to use spin unrestricted TDESMD to simulate the photofragmentation of teranitromethane molecule. So why we are interested in this molecule? Well, there are lots of reasons. So first, because this colorful molecule have many applications. For example, they can be used as nitrating reagent and explosives. Also because there are many experimental studies on the photofragmentation of this molecule, but the theoretical studies are limited. And more importantly, because this molecule have very few atoms, so we can save lots of computational resources by studying this molecule. So here I show the basic electronic structure of teranitromethane. So this time I consider two cases. The first one is neutral teranitromethane. The second one is teranitromethane cation. So as we can see from the diagram, for the neutral system, the spin alpha and spin beta component are the same because of paired electrons. But for the cation system, spin alpha and spin beta component are different. So we applied TDESMD to simulate the photofragmentation reaction. We have the TDESMD trajectory. Next, we want to build the energy diagram so that we can have the activation energy for specific chemical reactions. However, we cannot build the diagram directly from TDESMD trajectory because the TDESMD trajectory generates hot intermediates with significant kinetic energy. So we have to apply a post-processing technique to artificially remove the kinetic energy of hot intermediates. So the diagram in the right shows the energy diagram after we apply the post-processing technique. So as we can see, the starting point is teranitromethane molecule, and we end up with gas phase components. We have three nitrogen dioxide molecules, we have one carbon monoxide, and we have one nitrogen monoxide. So this product is fairly consistent with experimental findings. And we can get the activation energy from this whole reaction. It is about 8 electron volts. And we can even summarize different reactions based on this diagram, as we can see here. Okay, so finally we can build the simulated mass spectrum from TDESMD trajectories. So here are some examples. So panel A shows the simulated mass spectrum based on neutral system. B and C shows the simulated mass spectrum based on teranitromethane cation. And D is the experimental electron ionization mass spectrum. So as we can see, the simulated mass spectra have some similarity with the experimental mass spectra. Of course, there are some differences. And for the spectra A, we can see the parent eye is quite strong, but for B and C, the parent eye is quite weak. So this indicates the cation is much easier to fragment than the neutral. Okay, so here are my conclusions. So we have used TDESMD simulations to study the photofragmentation of left-eye cyclopentodiene complexes, and we found that our simulations reproduce the features of the experimental mass spectrum. The combination of photoionization time flight mass spectrometry and the TDESMD simulation provides a powerful tool to understand the photochemistry of left-eye organic complexes. And recently developed spin unrestricted TDESMD method has the potential to model and monitor photoreaction with open shell intermediates and radicals. And finally, we can extract the simulated mass spectrum from TDESMD trajectories and compare with experimental results. Yeah, that's all.
Thank you. So, what are the questions?